guys? I'm Austin Trahan.
I'm David Spurlock.
And we're mechanical engineers at Lamar University, and we're here at the Gladys City Boomtown to show you how to apply the flow rate equation from FluidMechanics and the spindle top that they have over here.
Getting a little bit about the history of this place. It was founded in 1802 by a guy named Petilia Higgins. And when he came, he discovered this, and he basically drew a pipe down 1,100 feet to the ground, and he was able to get the oil to pump out for 9 days straight,
Reaching out almost over 175 feet.
This tower is actually 75 feet in the air, so the oil shot up 100 feet past that. And on that day, they actually lost 850,000 barrels worth of oil that day. So that's a lot of oil to lose, and that's a lot of money. So at that time, the price in oil went down to approximately like 3 cents, and water actually increased up because it hit the ground and it mixed in with the water. And so the price of clean water actually had to go up in price for people to be able to have clean water.
To actually be able to get the oil to shoot up that high, for FluidMechanics, you have to have two pipes. One a bigger size that goes into a smaller size pipe to increase that pressure and that change to be able to get it to shoot that high. So that is what we're going to be looking at today, and we should be able to show y'all a video of the water going off.
Water to go that high.
So we're here at the pipe right here, and so to use the flow rate equation, we already got the flow rate. It's 3,000 gallons in 2 minutes. So when we get to the whiteboard, we'll have to convert that into cubic meters per second. But while we're out here, we're going to take the diameter of this part right here and this part right here, so we can get the pressure change right here, which helps it go over 100 feet over the 75-foot spindle top. And so, as we can see right here, the diameter of the bigger part is about 9 inches. And then the diameter of this part is about 5 inches. So that'll be able to help us out find the pressure change. Because all we really needed to get was the diameter, which we can find the area of both sections. And then we already have the flow rate, so we just have to rearrange the equation to get P1 minus P2 by itself.
Alright guys, so here we are now with a model of the pipe that we just seen outside. And when we measured it, I know y'all seen the numbers we had, but we had to convert them into meters because when we measured it, it was in inches. And that's how we got these two numbers right here. Going over A2 over A1, we had to calculate that, and we got 0.3086 meters squared, which we have to plug into the equation. This is the given flow rate that we were given, 3,000 gallons per 2 minutes. And we also had to convert this into cubic meters per second, in which we got that number. And then A2, we had to calculate that alone because that's required in the equation over there. This is the density we're going to use because theoretically we would have to measure the temperature, and that would be a long process. So the density of water, we chose 1,000 kilograms cubic meter.
Alright, so the equation that we chose was the theoretical flow rate equation, which has Q equal to the second area times the square root of 2 times the difference in pressure, which is what we're going to be looking for in this area where the water flows through it, over the density times, in brackets, 1 minus A2 over A1. So that is why we have to get A2 over A1 here. So to be able to get the P1 minus P2 by itself, we just rearranged it like this. And then, so that left us with the flow rate squared times the density times what was in brackets, 1 minus the A2 over A1 squared. And then all of that is over 2 times A2, just the area of the second part. And so with all that information plugged in, being the flow rate 0.09464 squared times our density 1,000 times 1 minus 0.3086 squared, all over 2 times 0.0127 squared equals 22,121.659 pascals.
Given that information, this is something that is applied on a day-to-day basis in any plant that you're working at. So this is why all of this right here is important, especially if you're looking to have some knowledge while you're going inside of a plant. So this is all very Very useful.
So this is how you would apply something from FluidMechanics into a real world situation that you might use every day.
And in that note, thank you guys for watching, and have a great day.